In this series of videos, we're going to be covering a new topic. We're working on field theory. And to begin, we're going to talk about algebraic field extensions and also what's called a radical field extension. I didn't even bother putting it as a formal definition on these slides, but what a field extension is just when we have one field sitting inside another field. We have a handful of standard examples that we're really familiar with and some other examples that are perhaps less familiar but are a little more comfortable after a first semester abstract algebra course. The very canonical and standard well-known example is the rational numbers sitting inside the real numbers sitting inside the complex numbers. This is very familiar to us, at least since high school. Something that's a little bit more familiar just from an abstract algebra class is the rationals as they sit inside the rationals adjoin the square root of 2. Now, I think in my first semester abstract algebra course, I'm wicked enough to actually have you prove by hand that the rational numbers adjoin the square root of 2 is a field. But doing that by just showing that it satisfies the properties of the field is really tedious and pretty awful. What's very nice is that as a consequence of some of the work that we're going to do in these slides, you can come up with a much quicker, much less painful proof that the rational numbers adjoin the square root of 2 is a field that involves a lot less work. Another less familiar example, but an example that I've been doing over and over again in the videos, is if we take this set containing two elements, it's the coset generated by x cubed plus x plus 1, and then 1 plus the ideal generated by x cubed plus x plus 1. That collection of cosets, as it sits inside of this factor ring, the integers mod 2 adjoined x mod the ideal generated by x cubed plus x plus 1. We've seen that that's a field before. That's one field, and then this subset of these two particular cosets is another field. So that's an example of a field extension. And something we haven't covered a lot, but something that is somewhat useful or just good to remind yourself of. So if we start with any arbitrary field f, we can take a look at f square brackets x, f adjoined x, which is the polynomial ring with coefficients from the field f. And we can do that whenever we start with a field. And in general, when you look at f adjoined x, you are not going to have a field. You're going to have an integral domain. However, you can then look at the field of fractions of that integral domain, and then we would have a nice field extension here, going from that original field we started with all the way up to the field of fractions of that polynomial ring. Now, the next thing we want to define is the degree of a field extension. So recall that when we covered vector spaces, if we have nested fields where we have f contained in E, then we can think of the larger field as a vector space over the smaller field. And as a vector space, it has some sort of dimension. It could be infinite dimensional or it could be finite dimensional. What we're going to do is the dimension of the larger field when viewed as a vector space over the smaller field is going to be called the degree of the extension. And I'm going to denote it with these absolute value signs, E colon F. What I would say if this were group theory is I would say sort of the index of F inside of E. That's the notation that we're going to use. But here we're going to call that the degree of the field extension, the degree of E over F. Let's return to our examples that we started the slides with. I've sort of ignored the degree of the extension from the rational numbers to the real numbers. It happens to be the case that that's infinite dimensional, but that can be difficult to prove. However, the complex numbers are a finite dimensional vector space over the real numbers. That's because the set that just contains the elements 1 and I serves as a basis for the complex numbers over the real numbers. Since that is a basis, that actually tells us exactly the dimension of the vector space, or the degree of the field extension, and that's 2. Returning to our other finite example, for now I'm going to allow myself to use the shorthand I to denote the ideal generated by x cubed plus x plus 1 inside my polynomial ring z mod 2z adjoined x. When we take a look at the set, which is 1 plus I, x plus I, and x squared plus I, this actually forms a basis for that field z mod 2z adjoined x mod I over the smaller vector space, which was just I and 1 plus I. So that would be an example of a field extension of degree 3. And returning to that last example on the previous slide, when we take a look at this field of fractions of the polynomial ring f adjoined x, that's an infinite dimensional vector space over the field f. This is because when we covered vector spaces, we saw that even f adjoined x, that polynomial ring, when viewed as a vector space over f, that was already infinite dimensional, and the field f, the field of fractions f of x, is even larger than f adjoined x. Now, something that's hugely important, and something that you should have proved when you were working on your worksheet for vector spaces, is if you have some fields here. Let's say we have a tower of fields and it's got 3 fields. F is contained in K is contained in E. They're all fields. And let's suppose that the degree of E over K and the degree of K over F are both finite. Then it happens to be the case that we could view the total largest field E as a vector space over the smallest field F, and that's going to be a finite dimensional vector space. And what's more, we can say exactly what the dimension of that extension is. So we can say that the degree of the extension from E down to F is just taking the individual degrees of the extensions and multiplying them together. So again, I'm glossing over this fact because you should have proved it actually when you did your worksheet for vector spaces. But this is a really useful fact to know that sort of degrees of extensions multiply on their way up. Now the next thing I want to do is I want to define what it means to be an algebraic element of a field, a transcendental element of a field, and a radical element of a field. So again, let's look at some fields, f contained in E, and let's take alpha to be an element of the larger field E. We're going to say that alpha is algebraic over the ground field f if alpha is a root of some polynomial in the polynomial ring with coefficients in the ground field, so in f adjoined x. If no such polynomial exists, then we say that alpha is transcendental over the field f. Now, if you could take alpha and raise it to some positive integer power n, and then you get something that belongs to the ground field, then we're going to say that alpha is radical. So I haven't put examples on this slide in terms of writing, but I'll say them orally right now. An example of, let's take f to be the rational numbers, and let's take E to be the complex numbers. So an element that's algebraic is something like I. So I is a root of the polynomial x squared plus 1. So I would be an example of an algebraic number, so it's square root of 2. Something like pi or E is said to be transcendental. However, proving that pi or E is transcendental is actually very difficult. Then for an example of something that's a radical number, then you could take a look at something like the square root of 2. Square root of 2 belongs to the complex numbers because in fact it's a real number. If you square it, you get all the way down to that ground field. You get 2, which is a rational number. So square root of 2 would be an example of something that is a radical number. Similarly, the cube root of 2 or the eighth root of 2 or anything like that would be a radical number. So you're familiar with all these terms. We're just defining them generally, even if we hadn't taken the field f to be the rational numbers. And now let's move from this definition of what it means for an element to be algebraic or radical, and let's move this towards definitions for what does it mean for a field to be an algebraic field extension or a radical extension. So again, f and E are assumed to be fields. You should assume that that's true if I write f or E for the rest of these collections of slides. Assume that they're fields, but I'll try to have written it down in the slides every single time, or at least say it out loud. If the larger field, if every single element of the larger field is algebraic over the smaller field, then we will say that the larger field is an algebraic extension of the ground field. Now, next, let's suppose that the field E is actually f adjoined alpha, where alpha is a radical element. Then we say that E is a radical extension of f. So be careful when you're learning these definitions. Sometimes it's tempting to assume that the definition of an algebraic field extension is when it's f adjoined alpha for alpha an algebraic element, but that's not what it means. Algebraic is if every single element of the larger field is algebraic, but radical is just when you're of the form f adjoined alpha for alpha a radical element. Now, the last thing that I want to define is what's actually called a repeated radical extension. So let's suppose that we start with a field f, this is our ground field, and that we start attaching radical elements to f. So maybe we go from f up to another field by adjoining the square root of 2, and then we go from that field to another field by adjoining the cube root of 5, and then we go up again, and so on and so forth. So that's what we mean to be a repeated radical extension. If you can make a chain, start with f, let's call that f naught, and let's say it's contained in a field f1, contained in a field f2, and so on and so forth, all the way up through a field f sub k, which is the same as the field E. If we have this chain of fields, where each field is obtained from the previous field by just adjoining a radical element, then that's what's called a repeated radical extension of the ground field. And since that's quite a mouthful to say, just like principal ideal domain or unique factorization domain, we're going to abbreviate repeated radical extension by RRE. Now, before we move on and do something with those definitions, I want to give some motivation for why we're interested in fields that behave that way. So, it's no news to you that if f of x is equal to, it's the quadratic polynomial ax squared plus bx plus c, and let's just say for now that a, b, and c are integers, then the roots of f are given by the quadratic formula. Now, that's something that we all know and are very comfortable with, and I'm fairly certain you could stop an average person on the street and they could at least say that they know the quadratic formula even if they couldn't tell you what it was. And this is no news to us. People have known how to deal with quadratic polynomials since about 600 BC. So I have a very wide time range written here on the motivation page for when people learned to deal with quadratics, because it wasn't until this late 1500s that people really came to terms with what a complex number was, and so it wasn't until that late 1500s that we had the quadratic form for formula for solving quadratics, sort of as we know it. But people in 600 BC could tell you there's 2 roots of that polynomial, there's 1 root of that polynomial, there are no roots of that polynomial, and in the case that it had real roots, they could tell you what they were. Now, if f of x is what's called a depressed cubic, which is something of the form x cubed plus bx plus c, then it's also possible to write down a formula for what the roots of this polynomial are. And they're given by these expressions right here, a plus b, and then these 2 fractions we have with a plus minus sign. Those give 2 different roots here, right? Where a and b have these nasty forms that I've written down on the page. Now, it's not important for you to know what a and b are to know what this formula is for depressed cubics. The point is, it's possible. I can take a depressed cubic and I can come up with a formula that explicitly tells me what the roots of this polynomial are. Now, it's not pretty, but I can write it down. And notice what's involved in each of these letters. Again, not pretty, but all I've done is I've taken integers, I've added them, subtracted them, multiplied them, divided them, and then taken some roots, square roots, cube roots, etc. And I was able to piece together the roots of this cubic polynomial. Now I said it's a depressed cubic. It doesn't have the most general form that a cubic polynomial could have, but in fact, if you want to find the roots of a general cubic, it's enough to solve a proper depressed cubic to find these roots, and you'll be able to solve your original question. So in knowing this formula, you really and truly do know how to solve a general cubic equation. And similarly, it's even messier, and I wouldn't even put it up to try to impress you. There is a formula for finding the roots of a quartic equation, and both of these equations were known in their generality to mathematicians in the late 1500s, about the same time that we really solidly wrote down the quadratic formula. There's a really interesting history too behind the cubic equation of mathematicians and pride and challenging each other to puzzles to solve cubic equations. So this was really the hot topic of study at the time in the late 1500s. And once people understood the cubic equation and the quartic equation, the question was just, as it always is in math, onwards and upwards, right? Let's take the quintic. Let's see if we can find a solution for the quintic. And then, if we're being really ambitious, let's see if we can find equations for a polynomial of any degree. Maybe we can just solve, in general, how to write down the roots of a polynomial of degree n. And wouldn't that be awesome? And what would be even better is if there was a formula for doing this that only involved the methods and things that we saw on the previous page. maybe it would only use addition, subtraction, multiplication, and division. And then we have to allow for taking radicals, square roots, cube roots, fourth roots, and things like that. It seems only natural that if I'm dealing with a polynomial of degree 3, that maybe to solve it I have to take a cube root somewhere. But maybe that's all I should have to be able to do, is maybe I have to take a cube root, fine, maybe I have to take a square root, fine, but then I should be able to piece everything together with my standard set of operations. So is there a formula that does this? And it wasn't until about 1824 that Abel and Ruffini came up with a proof that said, alas, it is not quite so nice as this. In fact, it stops at the quintic, and that's why people were having a hard time with it. There's no general formula giving the roots of a quintic equation that involves only these operations: addition, subtraction, multiplication, division, and radicals. What I should say is that this was 1824, so this took a good 200 years for somebody to be able to nail down an answer and say, no, we're not going to be able to do this no matter how hard we try. What's even better, which is really awesome, is you see Abel Ruffini and you see this theorem hyphenated giving both of those mathematicians credit. They didn't work together. They both independently came up with a proof of this fact around the same time, around 1824. Now, the thing is that it's not called the Abel-Ruffini-Galois theorem, but Galois also came up with an independent proof of this fact. It wasn't anything like the proofs of Abel or Ruffini. And yet, somehow, he doesn't get credit. Well, first of all, he came up with his proof a couple of years later. It really and truly was independently done. His result was totally different, but also around this time, it wasn't very easy for somebody like Galois, who didn't know Abel or Ruffini, to get his hands on a proof of what they'd done to know that they had done it. However, Galois is one of these fascinating mathematicians that just never got his day in the limelight. So it's not surprising to me that historically he was just not given credit for this amazing and outstanding result. But if you talk to most people today, they realize that Galois was very much ousted in the statement of this theorem. And in fact, if you're going to look at a proof of the fact that there's no general formula giving the roots of a quintic equation, you look at Galois' proof, always. His proof is just better. It's totally different than what Abel and Ruffini came up with, and it's 100 times better. But nobody at the time understood what he was doing, and so people just thought it was nonsense. Today we know better, and today we say, yeah, he really was genius, and let's learn what he did. Before I stop with this collection of slides, which has really gotten long and out of hand, so I apologize, I wanted to relate that motivation back to what we did when we introduced these topics of radical and algebraic and repeated radical extensions. So from the quadratic formula, we know that if we have a polynomial, ax squared plus bx plus c, that if we were to take that discriminant, b squared minus 4ac, and take the square root, and if we allowed the square root of that to be included with the rational numbers, then we'd be able to express all of the roots of the polynomial ax squared plus bx plus c inside the field q adjoined the square root of the discriminant. So if we worked in a radical extension of the rationals, this particular radical extension of the radical extension of the rationals, then we would have all the roots of a quadratic polynomial. However, we had that formula for a cubic as well, and in a cubic equation we weren't so lucky as to be able to work in a radical extension. We had to go up to what was called that repeated radical extension. So if you want to go back in your slides and take a look at the equation for finding the roots of a depressed cubic, let's take d to be this nasty bugger b cubed over 27 plus c squared over 4, and then let's start adding the things to the rational numbers that we need in order to express everything in those formulas we had on the previous page. So let's start with our ground field being the rational numbers, and then we need to add on the square root of -3. That was in our formula on the previous slide. We also needed the square root of this thing that we've called d here, this b cubed over 27 plus c squared over 4. The other thing that we needed to add on was then these two, the a and the b. And the a was -c over 2 plus the square root of d, the cube root of that, and the b was -c over 2 minus this square root of d and the cube root of that. So we need to add those two things on as well. And once we have all of those things square root of -3, square root of d, and then these more complicated expressions for a and b, capital A and b. Then we would be able to express all the roots of this depressed cubic x cubed plus bx plus c. So all of the roots would lie in F4. F4 is not a radical extension of the rationals, but it's a repeated radical extension of the rationals. And inside this RRE, we would contain all roots of the depressed cubic. And this is what Galois was asking. Other people were trying to find fun little algebraic methods of solving the quintic equation, but Galois wasn't even looking at polynomials. Galois was looking at fields. He was looking at repeated rational extensions, repeated radical extensions of the rationals, and he was looking inside of these fields for roots of a quintic polynomial. And that's really the question that Galois was asking. That's a little bit of why at the time people thought he was crazy, because he wasn't even talking about polynomials, he was talking about fields and field extensions. And what we'll see in the slides that are to come is why it was okay for Galois to do this and why he was just concentrating on fields instead of looking at polynomials.